Nice. Second derivative test. So, there's another way to find local max and mins that is a little bit different. If you remember the first derivative test, we would find the first derivative set equal to 0, and then we'd make a little chart, see where the first derivative changes from positive, negative, and negative, positive to find our local max and mins. There's actually a bit of again, it depends on what you think, kind of a bit of an easier way. Okay. So, for example, I mean, if we look at this point right here, which I'm not drawing anything. So if we look at this point right here, we know that f prime is equal to 0. Okay, even this point here, f prime is equal to 0. All right. What is the second derivative equal to at that point? Not really like what sign does it have is what I'm asking, because that's what I'm really concerned about. So what sign does the second derivative have? So we went over this yesterday. Second derivative is going to be what when it's concave down? Concave down, brown, what's, yeah, negative. It will be negative, so this will be less than 0. Okay. Here we're concave up, so the second derivative will be greater than 0. So the idea here is we can find the first derivative. So we know that the first derivative, again, most time the first derivative will just be equal to 0. All right. But if we know the sign of the second derivative at that point, if we know we have a horizontal tangent line and we know that this is concave down, well, what kind of point is going to exist at the horizontal tangent line at a concave down portion of the function? Well, that is going to be your local max. So what kind of function, if this is concave up, will have a horizontal tangent line where it's concave up, and that'll be your local min. So the idea here is we're going to take the first derivative, set it equal to 0 to find our critical points, take the second derivative and plug in those critical points. If we get a positive, we know it's concave up, so we have a local minimum. If we get a negative, we know it's concave down, so we have a local max. That is the second derivative test. So all that's right here. Now, by the way, notice I did not mention anything about where the function does not exist. So again, it only works when f prime is equal to 0. Okay, so this does not work when f prime doesn't exist, so we're not worried about that. So suppose when f prime is equal to 0, then if the second derivative is greater than 0, we have a relative minimum or local minimum. If f prime is less than 0, then we have a relative max. So let's go through this. First derivative, f prime of x is equal to 4x cubed minus 4x. So we do need to find the zeros for this, so we set this equal to 0. Factor out of 4x, so we get x squared minus 1. Now this gives us 0, and this gives us x equals plus 1 minus 1. Now, there's not a lot of room here, so I'm going to tell you kind of try to write small, because we're going to have a lot of justification for our answers like we have been in the past few days. All right. So now that we have our values that we're going to plug in, we take the second derivative, so f double prime of x, so the derivative of this, which is 12x squared minus 4. And again, we don't need to factor, we don't need to solve, we don't need to do anything. What we're going to do is we're going to find f double prime of 0, f double prime of negative 1, and f double prime of positive 1. Now, because it's just x squared, whatever I get for negative 1, I should also get for positive 1, because no matter what I plug in there, I'm just going to get 1. All right, but 0 is pretty easy. That's a negative 4. Okay, positive negative 1, that's going to give me 12 minus 4, which is 8. Now, being that this is f of 0 is less than 0, f double prime of 0 is less than 0, is negative, this is going to be a local max. Okay, now let me phrase that, because there has been a lot of people that kind of get stuck with the fact, well, it's negative, it should be a minimum. The thing is, because it's negative, this is concave down. Okay, so if you think about, because it's negative, it's concave down, what kind of point am I going to have? I'm going to have a local max. Okay. Now, because these are both positive, these are both going to be concave up, which means I'm going to have a local minimum value. All right. So we have, again, you can write this however or wherever you want on here because there's not a ton of room. So we have a relative max at x equals 0. Now, I don't know what the max value is. To know the max value, I plug it in. It actually ends up being 0 if you do plug it in. Didn't ask for it. It just says find the relative extrema. Didn't say that to find the actual values of them. All right. All right. Now we do need justification. So our justification is 1. Oh, internet blinked. Give me a second. Right. So justification is 1, that the first derivative is equal to 0. So because f prime of 0 is equal to 0, and the second derivative at 0 is less than 0. We have relative mins at x equals, now you do, I don't know if they need to list them separately, but you may want to list them separately at -1, because f prime of -1 is equal to 0, and f double prime of -1 is greater than 0. And we have another, because I ran out of room, relative min at x equals 1, because f prime of 1 is equal to 0, and f double prime of 1 is greater than 0. Now, that was a nice kind of easy one to start with. See where they get a little more complex here. So use the second derivative test to find relative extrema for this function. Okay, only on the interval from 0 to 2 pi. Okay, so they are limiting this because otherwise this is a cosine function. It's going to go on forever. So first derivative. What is the first derivative? What is f prime of x? Well, that's just the square root of 2. That's just a coefficient, so that's square root of 2. Derivative of cosine is negative sine, so we get plus sine, or 2 sine of x. So again, we set this equal to 0. So the question is 2 sine of x. Subtract the square root of 2 over 2 sine of x. So we get sine x is equal to negative root 2 over 2. Now, root 2 over 2 we know is every pi over 4. So it's either pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. Where is sine negative? In the third and fourth quadrant. So that would be 5 pi over 4 and 7 pi over 4. So x equals 5 pi over 4 and 7 pi over 4. All right, so we take the second derivative. Now that's gone in the second derivative. Okay, so it's just going to be 2 cosine x. So f double prime of 5 pi over 4 is equal to 2 cosine of 5 pi over 4. Now, I'm not super concerned what the values are, okay? But, I mean, we do know pi over 4 for sine and cosine is root 2 over 2. What I'm really concerned is it's positive or negative. Now, 5 pi over 4 is in the third quadrant. Cosine is negative in the third quadrant. So that is going to be negative root 2 over 2 times 2. So we end up with negative root 2. Okay? So we'll just say negative root 2. And f double prime of 7 pi over 4, that is equal to 2 cosine of 7 pi over 4. That is going to be positive root 2 over 2 times 2, so positive root 2. So again, this is less than 0, greater than 0. So we have a, because it's less than 0, less than 0 is a what? Concave down. Greater than 0 is concave up. Again, to me, I still get them messed up. I still think, hey, less than 0 should be a minimum because that's just in my head. That negative is min, positive max. But you have to think of it in terms of concave down and concave up. When you have a concave down section, okay, you will have a local max. So we have a relative max at x equals 5 pi over 4 because f prime of 5 pi over 4 is equal to 0 and f double prime of 5 pi over 4 is less than 0. We have a relative minimum at x equals 7 pi over 4 because f prime of 7 pi over 4 is equal to 0 and f double prime of 7 pi over 4 is greater than 0. So that is the second derivative test. Now, on the test that's coming up, you may be asked to specifically perform, use the first derivative test, use the second derivative test. So you will need to know both. On the AP test, I don't know how they're going to ask. I honestly don't think they're going to care which test you use, okay? Because it really doesn't make a difference. So the thing is, you just need to show your work. So if you use the first derivative test, you do need to make that table with the intervals, okay, to show where the signs change from positive, negative, negative, positive, to find your local max and local min. And again, give your reasoning if you use the second derivative test. Well, this is a local max because the f prime of that value is equal to 0, and the values change from negative to positive around it. Okay. So make sure you know your two tests and know how to explain your answer. All right, last part of this lesson. If there's only one critical point and the CP is an extrema, max or min, then it is an absolute extrema. Which just makes sense. It just means like if you have a parabola, just x squared, you have an absolute max or an absolute min, depending on if it's opening up or down. So same kind of concept here. If we only have one horizontal tangent line, the only way to have only one horizontal tangent line is your end behavior on both sides go the same direction. So it never turns back around. So here we have a function. Oh, this is fun. What's the derivative of this? So this is product rule and chain rule. So the derivative of negative x is negative 1. So we get negative 1 e to the x over 4 plus, technically it's going to be a minus, because it is negative x. So we'll go ahead and just put minus x. The derivative of e to the 4x is e to the, e to the x over 4 is e to the x 4 times 1/4. So if you want to write that as negative 1 e to the x over 4 minus 1/4 x e to the x over 4. Now, Nice thing here is we can, if we want to find where this is equal to 0, we can factor out the e to the x over 4, or even the negative e to the x over 4. Right. X over 4, which is going to give you 1 plus 1/4 x. So what would x have to be in order to make this 0? X equals negative 4. Now, there is nothing that's going to make this equal to 0, so I don't worry about that. There's no value I can put in an exponent that makes something 0. Doesn't exist. So don't worry about that part. So just the parentheses. So again, we do only have one critical value or critical point. So we take the second derivative. So we're going to take the derivative of this part right here. Now, the nice thing about negative e to the x over 4 is that is going to be negative e to the x over 4 times 1/4. Minus, I'm going to put a minus 1/4 outside, and I'm just going to take the derivative of this again, which we kind of already know what that is, because we just did it right here. It is e to the x over 4 plus 1/4 x e to the x over 4. So because I took the negative 1/4 out, I didn't have to worry about the negative or the 1/4. All right, you can distribute that through if you want. Negative 1/4 e to the x over 4 minus 1/4 e to the x over 4. So that just combines to be negative 1/2 e to the x over 4. And that is minus 1/16 x e to the x over 4. Now, the idea here is we are going to plug in negative 4. So negative 1/2. Now, negative 4 just gives me e to the negative 1. Minus 1/16 times negative 4, e to the negative 1. So we end up with negative 1 2e plus 1/4 e. So that is going to be, we make them the same fraction, multiply it by 2, we get negative 1 over 1/4 e. So, positive or negative? Greater than 0, less than 0. This is less than 0, which means this is a concave down function. So we have a local max. So we have a absolute max at x equals negative 4 because f prime at negative 4 is equal to 0 and f double prime at negative 4 is less than 0. All right. Now, any questions in the first part? This next lesson looks really short, doesn't it? I'll bring that up because it's going to be probably one of the most important lessons in this unit. Okay, probably one of the more challenging lessons in the unit. Okay, the idea of what we're going to do is we are going to try to either graph a derivative function or graph the original function if we're given the derivative. Okay? Now, graphing a derivative function isn't really that bad. real challenging part is doing it backwards. Okay, and I'll explain in a moment why that is. Now, the idea here is, again, one, just make sure you do note this is super important, especially if you're taking the AP exam. All right. So we're going to focus on the slope because, again, if I'm trying to graph the derivative, what I'm looking for is the slope of f. Okay. Because the slope of f is the y value of f prime. Now, just like we did the other day, I think we did this the other day, we had a function and we are looking at how a function is changing. Here we have a really positive slope, really big positive slope. It is very positive slope here. And as we progress, that positive slope is getting less positive, less bigger, smaller, smaller, and smaller until it reaches 0. Now, after that, we have a negative slope, and that's getting a little bigger, 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 biggest right here, okay? And then it's getting back to smaller, 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 until it is 0 again. Now we go back to getting positive, bigger, 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 and bigger. Now, two of the most important things on here is where we have zeros. Because where we have those zeros, that's where the derivative will cross the x-axis. That's where the derivative is equal to 0. Again, the value of the y value for the derivative is the slope. So when the slope is 0, that's where the derivative is 0. All right. Also, what's going to be important is the fact that right here where we have that highest negative value, that is going where we have that's technically, if you look at it, is an inflection point where the function changes from concave up to concave down. That is going to be the turning point. Now, again, I don't know exactly what value that is. I do know it's negative, so it is down here. So I'm just going to put a value down here. I don't know exactly what slope that is. I'm just going to pick an arbitrary value. If I had a function, then that would be easier, but I don't. Okay. So here we have a very positive value, and it's getting smaller and smaller and smaller until it gets to 0. We have negative values until we get the highest negative, and then it's back to going less negative until it is positive again. Now, what kind of function did we end up graphing? When you can tell me the shape of that function, the purple graph that we just graphed is what? It's a parabola. Yes, it's a parabola. Okay. Why does that make sense that that's a parabola? Well, if I just had x cubed as my function, what is the derivative of x cubed? Hey, it's a quadratic function. So every time we take a derivative of a function, it goes down by 1 degree. Okay, so if we did the derivative of that, so if I had a parabola as my graph, then my derivative would end up being a linear function. Okay, so that is something that will be helpful. Now, will that be helpful every single time? Well, let's say you had this graph. It's the graph of that. You might know what function that is. I'm joking. Nobody knows what that is. I don't know what it is. I just made it up. Okay, so that's where you're going to have to take the fact that here, at this point, is going to be is where it's going to cross the x-axis. There it's going to cross the x-axis. Here, I'm going to have inflection point here and here. Okay, another kind of weird inflection point here and here. Okay, so yeah, you're going to have to take all the concepts that we just talked about and do your best. Okay. Now, that's also true forwards and backwards. Okay, so let's look at the derivative function. Here we have a derivative function. Okay, what do we know what the derivative function tells us? The graph of the derivative function tells us a couple things. Okay, one, we know where the derivative equals 0. All these points right here, those are generally going to be turning points. Okay, points where your function's a local max or local min. Now, how do I know if it's a local max or local min? If it's going from negative to positive, if I'm decreasing to increasing, that's a local min. I'm going from positive to negative, that's a local max, and this is a local min. All right. Now, where I have my horizontal tangent lines, like we said right here, at point of inflection, so this is a point of inflection, I'm just going to abbreviate that. Same here, point of inflection. Now, here's the hard part about derivatives. Off the side here, I'm just going to say, what is the derivative? If I had f of x is equal to, let's say, this is a cubic function, so we'll do a quartic function, x squared plus 2, or x to the fourth plus 2. What's the derivative of that? Well, that'd be 4x cubed, right? All right. Now, let's take another derivative. If I had f of x is equal to x to the fourth minus 1,000, what's the derivative of that? It's the same, right? 4x cubed. The hard part about derivatives, and we'll learn more about this in the later chapters. Okay, the hard part about doing this with derivatives is we do not know where the constant is. We do not know the y-intercept because the y-intercept is gone when you take the derivative. So we just have to do the best you can, which means when you do the homework and you draw your graph, as long as your graph resembles the answer key, just shift it up or down, you're good. Okay, because it just depends on where you're going to pick your arbitrary y-intercept. Okay, so as long as you have one, all your mins and max match, all your points of inflections match, you're fine. Okay, just because the curve is extended on the homework or not as extended as much as you did on the homework doesn't mean you're not correct. Right? So now, again, I'm going to start here. I know I have a local min. I don't know. I'm just going to pick a value down here. Okay, I know I'm going to have a local max. I'm just going to pick a value up here. Another local min, say a little lower this time, a little higher. All right. Right here, I'm going to have a point of inflection. So somewhere around here, it's going to change from concave up to concave down. Same right here, I'm going to have a point of inflection where it changes from concave down to concave up. So there we go. So I would definitely make sure you label, not label, but highlight the points, and you could label your points as well for your max and mins and your points of inflection when you draw this graph. All right. There's one more thing I want to show you, just because you should know this, and if you're allowed a calculator, then you should know how to use your calculator. Your calculator will actually graph derivative functions. So I'm going to show you how to do that. We are going to take a function. Let me go here real quick. Just delete that. So we're going to take this function. So go ahead and plot this function in your calculator. Okay. You graph that just to show you what it looks like. So it's kind of a pretty crazy function. Yeah, look at that. So back to y. Now, we are going to do the derivative just like we do a derivative if we're trying to find the actual derivative of a point. We're going to go to math and the derivative and have that set up. Now, you could type in sine e to the x, but you don't have to. Okay. What you can do is there is a button called variables, VAR. It is right beside your clear button. Okay, variables. And you want to scroll over to y variables. All right. Now, my y variable starts at y0. Yours most likely starts at y1. So that's what you're going to use y1. I'm going to use y0. And all it says is I'm going to take the graph of my first function and put it in here. Okay, so again, that is math, your derivative in derived function, then variables. Scroll over, because I start here, table, dot, changing table, all that fun stuff right there. Scroll over to y variables. Choose your correct y variable. Again, I start at y0. You may start at y1. Now, because we don't want to do this at a point, we are just going to say x is equal to x. That way we get every single point. And that is it. If you graph, you will see, and mine has it in red and blue. My red function is my original. My blue is my new function. Again, yours may be different colors. So if we graph, here we have the red, the original function, and the blue is the derivative. Which gets pretty crazy there. Yeah, pretty crazy. Pretty quickly too. So there you go. There's how you can graph your derivative function. In case you ever want to look at it. In case you need to look at it for some reason. Again, what we can see with this is, again, my red is my original function. Right here, all right, at this, I can't really draw in here, but I guess I can. Right. Minimize you. So right here, I have a local max. Hey, that's where it crosses the x-axis. So right here, I have a local min. That's where it crosses the x-axis. Again, max, cross, min, cross, max, cross, min. Again, there we go. We can see right about here is where I have a point of inflection. So that's where my function, my derivative will have a horizontal line. Same thing here. So right here, I have a point of inflection. So yeah, there's all your stuff. That's it for the day. So any question? All right.